Have you ever stopped to think, really think, about how we understand the super small...
The quantum world, yeah. It's definitely out there.
It really is. And sometimes the simplest ideas, well, they turn out to be the most profound. Today we're doing a deep dive into exactly that, probability amplitudes.
And straight from Richard Feynman, no less, we're looking at the Feynman Lectures, Volume 3, Chapter 3.
You've shared some amazing stuff from there. It's quite a ride.
It is. And what's fascinating right off the bat is Feynman himself calls this a pedagogical experiment.
Meaning?
Well, he's sort of flipping the script. He starts with what most people think are the advanced bits of quantum mechanics.
Why do that? Seems counterintuitive.
Because he thought the math, the actual structure underneath those bits, was surprisingly simple, more fundamental in a way.
Okay, I'm intrigued. So our mission today, cut through the usual complexity, get to the heart of these probability amplitudes.
Figure out how they combine, how they work.
And see how they explain some really, really weird quantum stuff. Get ready for some potential aha moments, because this genuinely changes how you picture reality.
Absolutely.
So how does Feynman kick this off? He just dives straight into these probability amplitudes.
Yep. Forget simple odds for a second. In quantum mechanics, we're dealing with these things called amplitudes. They're complex numbers.
Complex numbers, like with imaginary parts.
Exactly. Think of them like little arrows almost. They have a length or magnitude and a direction or phase. That's an amplitude.
Okay, little quantum arrows.
Yeah.
Got it. So what's the first rule?
The first big principle is how you get from that amplitude to an actual measurable probability, the chance of something actually happening.
Right.
It's not the amplitude itself. You have to take the amplitude's size, its absolute value, and square it. That number is the probability.
Okay. Probability is the amplitude squared. Simple enough, maybe.
Well, it gets interesting fast.
I bet it does. Let's talk about the classic example, the two-slit experiment. An electron, say, heading towards a screen with two slits in it.
Right. Classically, you'd think, okay, chance of going through slit 1 plus chance of going through slit 2. Add them up.
But quantum mechanics, not so much.
Not so much. And this hits the second key idea. Why don't probabilities just add up like that?
Yeah, why not?
Because, and this is crucial, if a particle can get to the same final spot through two or more ways that are fundamentally indistinguishable.
Indistinguishable, meaning you absolutely cannot tell which path it took, not even in principle.
Exactly. If the paths are indistinguishable, then you don't add the probabilities, you add the amplitudes, the little quantum arrows.
Ah, okay. So for the two slits, there's an amplitude for going through slit 1 and an amplitude for going through slit 2.
Yep. And the total amplitude to reach a point on the screen is the sum of those two amplitudes. Add the arrows, head to tail, sort of.
And then you square that total amplitude.
Then you square the result to get the probability. And because amplitudes can point in different directions, adding them can lead to them reinforcing each other or canceling each other out.
Which gives you those interference patterns, the bright and dark bands.
That's it, exactly. It's the adding of amplitudes for indistinguishable paths.
Okay, that's huge. But what about building up the amplitude for just one of those paths, like from the source through the slit to the screen?
Good question. That brings us to the third rule. When a process happens in steps, one after another.
Like going from source to slit 1, then from slit 1 to the detector.
Precisely. For a specific sequence like that, the total amplitude for that entire route is the product of the amplitudes for each individual step.
So you multiply the amplitude for the first leg by the amplitude for the second leg.
You got it. Amplitude Espit-Ganser times amplitude assessore, read right to left, like the events unfolding.
Okay, multiply for steps in sequence, add for indistinguishable alternatives. Let's try to scale this up. Imagine something more complex, like a particle going through two walls, maybe.
Yeah, say the first wall has 2 holes and the second wall has 3 holes.
Okay. How many ways can it get through?
Well, 2 choices at the first wall, 3 at the second. That's 2 times 3, so 6 possible distinct routes from source to detector.
It's routes. Wow.
And the total amplitude to get to the detector is the sum of the amplitudes for each of those 6 routes.
And each of those 6 amplitudes.
It is itself a product.
Yeah.
Product of 3 amplitudes.
Yeah.
Source to first hole to second hole to detector.
You can see how it builds up. It's like combinatorial.
It really is. This framework, these 3 simple rules, let you calculate incredibly complex things.
But there's a catch, right? Feynman mentions this wave function idea.
Ah, yes. We talk about wave equations, wave functions,
Yeah.
but he's very clear. This wave function, this amplitude spread out in space, it's not like a real wave.
Not like a water wave or sound wave?
No. You can't picture it as a physical ripple in space. It's an abstract mathematical thing, a tool for calculating probabilities. Hugely successful, but abstract.
That's a pretty mind-bending detail right there.
It is, but what's really elegant, and maybe what Feynman meant by easy, is how these amplitudes work. Once you know the amplitudes for a particle to have reached, say, the holes in that first wall,
Yeah.
you don't need to know anything more about where it came from before that point to predict where it's going next. The amplitudes at the intermediate stage hold all the necessary information.
Okay, that simplifies things in a deep way. So indistinguishable paths mean adding amplitudes.
Yeah.
Got it. But what if we can tell the paths apart, or if we try?
This is where observation comes in. Back to the two-slit experiment, but now imagine we put a light source near the slits, trying to see which slit the electron goes through.
Okay, so we're trying to watch it.
Exactly, and the act of watching involves interaction. Maybe a photon bounces off the electron. Now, there's an amplitude for a photon to scatter if the electron goes through slit 1, let's call it A.
And another amplitude if it goes through slit 2, say B.
Well, yeah, but it depends on the light. If the light's wavelength is very short, like a high-energy photon.
It gives a really precise measurement.
Yes. It can tell you definitively, aha, the electron went through slit 1. In that case, the amplitude B for scattering if it went through slit 2 is essentially 0. You know the path.
And if you know the path,
the paths are now distinguishable, so you don't add amplitudes anymore. The interference pattern vanishes. You just get the pattern you'd expect if only slit 1 was open.
what if the light wavelength is long? Fuzzy detection.
If it's long, the photon scattering doesn't tell you clearly which slit it was. The amplitudes A and B might be similar. You can't distinguish the paths effectively. And so the paths become effectively indistinguishable again, and the interference pattern comes back. Our ability to get that which path information is what kills the interference.
That is wild. The potential to know changes the outcome. Okay, here's a potentially tricky bit. What if you set up detectors for the scattered photons, one behind each slit, D1 and D2? You run the experiment. You find an electron at your screen, and you detect a photon. Maybe it was at D1, maybe D2, but you decide, I don't care which detector clicked. Do you add the amplitude for electron at X, photon at D1, to the amplitude for electron at X, photon at D2?
Great question. And the answer is a definite no.
No. Why not? I chose not to look.
Doesn't matter what you choose. The rule is absolute.
Yeah.
You must never add amplitudes for different and distinct final states.
A photon at D1 is a different final state from a photon at D2.
Absolutely. They are distinguishable outcomes in principle. Nature recorded which detector fired, even if you ignore the data.
So how do you calculate the probability then, if you don't care which detector fired?
You have to calculate the probability for each distinct final state separately. First, find the probability of electron at X, A, and D, photon at D1. That involves squaring the relevant amplitude, like a Becher, perhaps. Okay. Then you find the probability of the other distinct final state, electron at X, A, and D, photon at D2. Square its amplitude, maybe at Br.
Right. Two separate probabilities.
And then, because those are two distinct, mutually exclusive final possibilities for the whole system, you simply add those probabilities together.
Add the probabilities, not the amplitudes, because the final states were different.
Exactly. P total equals P photon at D1 plus P photon at D2. And this calculation perfectly matches the experimental results where observation destroys interference. It's not magic, it's just following the rules of amplitudes and probabilities.
Okay, that rule about distinct final states is critical. Let's push this further. Neutrons scattering off a crystal. Sounds significantly more complex.
It can seem that way, but the principles we've just discussed, they apply directly.
All right, so neutron hits a crystal.
Imagine the neutron scatters off the different atoms, the nuclei, inside the crystal lattice. Now, if the scattering happens without disturbing the atoms, no energy change, no spin flip, nothing.
Meaning you can't tell which specific atom the neutron bounced off.
Precisely. The paths scattering off atom A, scattering off atom B, scattering off atom C are indistinguishable.
So rule 2 applies. Add the amplitudes.
You got it. Add the amplitude for scattering from each atom, then square the total. And just like with light from a grating, this leads to sharp interference peaks. Certain directions get high probability, others low. That's Bragg scattering, essentially.
Makes sense. But the source, Feynman's lecture, mentions a puzzle. Sometimes you see those sharp peaks, but also, like, a general smear of scattering in all directions underneath. A background haze.
Yes. That puzzled physicists for a while. If the scattering is just simple interference, why the background? What else is going on?
What is going on?
Often the answer is spin.
Spin again, like the electron's intrinsic magnetism.
Exactly. Neutrons have spin. And crucially, the nuclei in the crystal often also have spin. This adds another layer.
Okay. How does spin change things here?
Well, consider a neutron scattering off a nucleus. If their spins happen to be aligned, both pointing up, say the scattering can happen without flipping either spin.
No spin flip. So nothing changed that marks which nucleus it was.
Correct. If no spin flips, you still can't tell which nucleus did the scattering. The paths remain indistinguishable.
Amplitudes add sharp peaks. Same as before.
Right. But what if the neutron spin is up and the nucleus spin is down? They're opposite.
Yeah.
Now, the scattering interaction can cause a spin flip. The neutron spin might flip down, and that specific nucleus's spin flips up to conserve angular momentum.
Wait, if one specific nucleus flips its spin,
Then you could, in principle, go into the crystal afterwards and find that one nucleus whose spin is now different. You'd know exactly which atom scattered the neutron.
so that path, the one involving the spin flip, is now distinguishable from a path where no spin flip occurred or where a different nucleus flipped its spin.
Precisely. The final state, neutron scattered plus nucleus A flipped, is distinct from neutron scattered plus nucleus B flipped.
And the rule for distinct final states is?
You add the probabilities, not the amplitudes. So the probability of scattering with a spin flip off atom A plus the probability of scattering with the spin flip off atom B, and so on.
And adding probabilities like that doesn't create sharp interference peaks, does it?
No, it gives a much smoother distribution. Just a general background scattering.
So the actual experiment, where you just detect neutrons without checking their spin or the crystal spin state.
You're essentially collecting data from two different kinds of processes happening simultaneously. One process is scattering without spin flips that gives the sharp interference peaks because the paths are indistinguishable.
Okay.
The other process is scattering with spin flips. Since these paths are distinguishable, in principle, by which nucleus flipped, you add their probabilities, leading to the smooth background.
So the total pattern is the sum of those two outcomes. P total, P, no flip, interference, plus P flip, no interference.
Exactly. Sharp peaks sitting on top of a diffuse background. It's a beautiful confirmation of the core principle. Distinguishability determines whether you add amplitudes or probabilities, even potential distinguishability.
Man, that really nails it down. Indistinguishable paths, add amplitudes.
Yeah.
Distinguishable paths, add probabilities. But what about the particles themselves? What if they are identical?
Ah, yes. The final twist. Identical particles. This leads to some truly non-classical behavior.
Okay, let's take an example. Say alpha particles, helium nuclei scattering off oxygen nuclei.
Right. Alpha and oxygen are clearly different. Your detector can easily tell them apart. So if you place a detector at some angle,
it might catch the alpha particle that bounced off, or it might catch the oxygen nucleus that got knocked forward.
Correct. Two distinct possibilities. The detector seeing an alpha is a different final state than the detector seeing an oxygen.
Distinguishable final states. So
That's
add probabilities.
Add the probabilities. Calculate the chance of scattering the alpha to that angle. Calculate the chance of scattering the oxygen to that angle. Add them up. It matches classical intuition pretty well.
Okay, seems straightforward.
Okay.
What if you scatter alpha particles off other alpha particles?
Yeah.
Alpha on alpha.
Now it gets weird because alpha particles are identical, fundamentally indistinguishable.
So if your detector at, say, 45 degrees catches an alpha particle,
you have absolutely no way of knowing if that's the original alpha particle you shot in, which scattered at 45 degrees, or if it's the target alpha particle that got knocked forward to 45 degrees.
Two possibilities leading to the exact same outcome, an alpha particle in the detector.
Exactly. And because you cannot, even in principle, distinguish these two scenarios.
Rule 2 again. You have to add the amplitudes for those two processes.
You have to add the amplitudes. The amplitude for the projectile scattering to angle theta, plus the amplitude for the target scattering to angle theta, which turns out to be add beta, and then square the sum. Phi plus phi. This interference term makes the scattering probability very different from the classical expectation, especially around 90 degrees, often higher.
Wow. Just because the particles are identical, does this positive interference always happen with identical particles?
Not always, and this is where it gets even stranger. It depends on the type of identical particle. Alpha particles are bosons, but particles like electrons or protons are fermions.
Fermions. They obey the Pauli exclusion principle, right?
They do, and they have another peculiar rule when scattering off each other. Let's take electrons scattering off electrons.
Okay, still identical particles, still two indistinguishable ways to get an electron in the detector at angle theta.
Right, but if the two electrons have their spins pointing in the same direction, parallel spins,
Yeah.
then the amplitudes for the two paths, projectile scatters to theta or target scatters to theta, interfere with a minus sign.
A minus sign. So you subtract the amplitude.
You subtract them. The total amplitude is... So the probability is first. This destructive interference can make the probability much lower than classically expected in some directions.
That is bizarre. Why the minus sign for identical fermions with parallel spins?
Well, it's a fundamental postulate of quantum mechanics related to the symmetry requirements of the wave function for identical fermions. Deep stuff. But it's a rule that nature follows.
Okay, what if the electrons have opposite spins? Anti-parallel.
Now think about it. If one spin is up and one is down initially, and you detect an electron with spin up at your detector.
You know, it must have been the original spin-up electron, right? Because spin is generally conserved in the scattering.
Exactly. The spin acts like a label. You can now, in principle, distinguish whether the detected electron was the projectile or the target.
The paths become distinguishable because of the spin information.
Correct. And if the paths are distinguishable...
You add the probabilities. No interference term. Just phi.
Precisely.
So for a real beam of electrons, which is usually unpolarized, a mix of spin states.
You have to average over the possibilities. Half the time, maybe they have parallel spins, giving half the time anti-parallel, giving phi plus phi. You average those results.
And the final result?
For electrons at 90 degrees, for example, the result turns out to be half of the classical prediction. These identical particle effects are just fundamentally quantum, no classical analog.
What an absolutely incredible journey through these core ideas. We started with Feynman's slightly unconventional approach.
His pedagogical experiment.
Yeah. And what we've really landed on is this incredibly powerful, maybe counterintuitive core rule of quantum mechanics.
It boils down to distinguishability.
Right. If alternatives, paths, particles, whatever, are fundamentally indistinguishable.
You add their quantum amplitudes. Interference happens.
But if they are distinguishable, even just in principle, even if you don't check,
then you calculate the probability for each distinct case and add those probabilities together. No interference between those cases.
And connecting this back, it really highlights how the potential for knowing something in the quantum world fundamentally changes reality.
It's not about consciousness or human observers necessarily. It's about whether the information to distinguish paths exists anywhere in the universe. Even if it's just a flip spin in a crystal, nature keeps track.
And this isn't just, philosophical musing. These rules are the bedrock. They explain how transistors work, how stars shine, how materials have the properties they do.
It's the fundamental operating system of the universe, as far as we can tell.
So next time you think about waves, particles, reality itself, remember this key idea: indistinguishability, and the strange, beautiful consequences it leads to.
Adding amplitudes versus adding probabilities. It's the heart of quantum mechanics.
Definitely. So here's a final thought to leave you with. We've seen how critical indistinguishability is for particles. Could this principle, this way of thinking about combining possibilities when identities or paths blur, apply elsewhere? Maybe in complex systems, information theory, or even other areas we haven't considered. What other mysteries might be hiding, just waiting for us to figure out their underlying amplitudes?